Good morning, everyone, from the snowy Munich. It's a great pleasure to welcome you to another QBN webinar. This time we will talk about diamond-based quantum technologies for mobile applications. NV centers and diamonds as tiny tips for scanning microscopy, I think, are well-known applications, but you can do much more with diamonds. To be honest, who doesn't like to work with diamond? I think everyone loves diamonds on a ring or for a better blade or drill, but most awesome is to use it for quantum technologies from my point of view. So I did in my diploma thesis a short review. This is me in the lab of Ferdinand Schmidt-Kahler at the University of Mainz here in Germany, and I built a setup for ODMR, so optical detection of magnetic resonance, with a GSD microscope, and the aim was to deterministically implant single NV centers in diamond to use them later as a quantum register. So you can see here the setup, also the tip from a scanning microscope and single NV center, and the Zeeman splitting, and also some spin gymnastics. Here is the Rabi oscillation. At that time, I'd loved to found a startup based on quantum technologies, but yeah, it was more fundamental research. So instead, I worked in a cluster management of an photonics cluster and as an innovation and company builder after that. And now I'm more than happy to build a European quantum business network for quantum technologies in general. So I think a network is more than an ecosystem. So in an ecosystem, every person and every organization is in charge of their own partnerships, of their own developments, of their own business developments. And adding a cluster management that supports all stakeholders in this ecosystem and manages the collaboration processes within the ecosystem provides an additional value. I started QBN last year in May with the aim to build Europe's best quantum business network to transform the quantum community to a strong quantum industry. Therefore, we support networking, of course, collaboration. We provide startup support, marketing support, like these QBN webinars, or the European Quantum Leadership Sessions. We have a quantum job board. We provide business development support. We provide fast access to public and private funding, and also have some individual support services. As a key element of our network activity, we have the QBN webinars on the different subfields of quantum technologies like sensing, imaging, and metrology, simulation, communication, computing, and also the enabling technologies like photonics and nanoelectronics. So with this colorful bunch of activities, we want to support our members and the community in general. And I want to invite you to join the growing network to transform the community to an industry together. Here are a few save the dates for the upcoming meetings and webinars and European Quantum Leadership Sessions. I think the next one is in February, the 10th of February, the European Quantum Leadership Session 2 on quantum communication. I think this is going to be another very great session. So back to the webinar. A few points. This webinar is being recorded. You can watch it on the YouTube channel of QBN on demand. If you have questions, just put it in the Q&A. And if you have further questions afterwards the webinar, don't hesitate to write me an email. And now let me introduce you to Gabriella. She will moderate the webinar with me today. Gabriella, do you want to say a few words?
Good morning, everyone, from Oxfordshire. I'm Gabriella. I work at Element 6 for strategic marketing and business development for diamond-enabled technology. And I'm pleased to be here today.
Perfect. Thank you very much. So then we can start with the first speaker. The first speaker is Matthew Makeham, principal research scientist. He has been with Element 6 for 13 years now, if I'm right. So I can say he's a real expert in what he's doing. And today he will share his expertise in engineering diamond for quantum technologies. Matthew, the stage.
Okay, thank you, Hannes. All right, let me just share my screen and get presentation underway. 2 seconds. Okay, so hopefully you can all see my screen now.
Yeah, perfect.
Yes. Okay, so as you have said, I'm Matthew Markham from Element 6. As he said, I've also been at Element 6 for a long period of time now, working on this area of diamond quantum technologies. So what I'm going to talk to you about today, I'll give you a sort of a brief introduction to the NB defect. It kind of says, sort of, flavour some of the things, but I'll give you a very sort of a basic overview of the NB defect and why that's useful and kind of how it works. I'll then go in and talk about what we do as our core, which is basically developing materials, talking about some of the sort of key things to consider when choosing a material, and also the different types of materials that we make, along with thinking about what has to be key to this is making material that you can scale, material that you can produce time and time again, so that when you want it for your quantum application, it's repeatable. And then I'm going to go on, and I've got 3 case studies to talk through to basically just give you a flavour of the different things that you can do with diamond. Okay, so the NV defect, nitrogen-vacancy defect on diamond. So first of all, what is it? So it's basically consists of a nitrogen in the crystal lattice next to a vacancy or a gap in the lattice, forming this NV defect. It's a particular charge state that you were interested in, the negative charge state of the NV defect. The neutral charge state is also a stable charge state as well. What's very unique about this defect, it has this very interesting energy level structure, such that when you shine green light on it, so green laser light or LED light, an LED, if you start in the 0 state, you basically cycle up to the excited state and then back down with the emission of a red photon, or you can start in the plus or minus 1 state, and then you actually go by this singlet state back into the ground state, thereby having a mechanism to spin polarize within the diamond. What you can then do is apply microwaves, and you can then flip it between these states, create a superposition, and manipulate the spin as to how you want to, whatever state you want to put it in. And then you can then also read out that defect simply by measuring the amount of red light that comes out of the diamond. So whether it's in a bright state or dark state tells you whether it's in the ms equals 0 or ms plus or minus 1. So you've got this optical readout. So all sort of very simple science. Then obviously these levels, the ms plus minus 1 states, they're affected by Zeeman splitting. You can see that in this plot here, where basically you apply a microwave field. Once you hit resonance, you get this dip, which is obviously associated with this basically meeting this energy gap criteria, and then dropping into the ms plus minus 1 state and having a lower fluorescence. And then application of a magnetic field splits these 2 energy levels, which you can see here. And as you increase the magnetic field, that splitting is proportional basically by these fundamental constants multiplied by the magnetic field. So you have a very simple magnetic field system, magnetic field sensor. And the NV defect, it can exist along 4 different axes. So you actually have 8 pairs of lines typically within a system, because you have all NV defects along all the different 4 orientations. And what's particularly unique about diamond is it does this at room temperature. So most other quantum materials, if you like. You'd have to cool down to liquid nitrogen or liquid helium temperatures to see these sorts of effects, but because of the unique properties of diamond, you're able to see these at room temperature. So what are people thinking about doing with these things? Well, there's lots of different applications. I'm going to talk about today just on the magnetometry side of things, but you can also do lots of different types of sensing. So things like thermometry, so using it as a temperature sensor. We're going to hear today from Quantum Brilliance. They're going to talk about quantum computation. And then you can also do other things such as making mazes, and I'll talk about that later. But what's pretty unique there about Diamond is you get to cover all these applications with the one platform material. So what does an actual device look like? This again is another strength, I think, of Diamond, is that the actual devices are pretty simple. You can cobble together a system using very simple off-the-shelf components. Obviously, making an engineered device, you use something more complicated, but in principle, all you need is a green light source. That can be a laser or an LED. Obviously, some optics to couple the light into the diamond. Your diamond obviously containing the nitrogen-vacancy defect. You then need some kind of RF source to apply to your diamond to manipulate the spin state. You need a static magnetic field, and that's just to separate out the different contributions from the 4 different orientations of the NB defect. And then you need to basically just collect the red light coming off, so some kind of filter and detector. And you can see that in this little video here, where basically shining, this here is the diamond, we're shining the light on the diamond and flipping the spin state, and you see this blinking. So you can see all this stuff at room temperature relatively simply. So what does that mean for magnetic field sensing? Put it into sort of more device and how to maximize the performance. So it's really these 4 factors here. Contrast, which is basically the amount of useful light you're getting out of the diamond. So light from, say, for example, from NV0 is actually parasitic. It doesn't actually contribute to the signal that you're trying to measure. Things like collection efficiency, the amount of light actually collecting out of the diamond, the useful light. And these 2, which are somewhat coupled, which is the number of NV defects that you're using and the spin coherence time. Now, for a finite or a sample of a particular size, you can increase or decrease the number of NV defects, and that has an effect on T2 star, the spin lifetime. So the more NV defects you have, typically the shorter the spin lifetime. And that's where you then have to start to think about the device. How are you going to build this system? And this is a nice paper back in 2015 where they looked at using diamond in what they call a light trapping diamond waveguide, where by it bouncing the light around the diamond, you were able to maximize the usage of the NV defects. And the advantage of that is you can have your NV defects spaced far apart. The downside of that is, how do you apply your RF field and your uniform static magnetic field uniformly across this diamond, which is where other approaches, such as having a single pass approach, have an advantage. So you really need to think about the device architecture and the diamond properties as sort of as a single unity thing, rather than trying to just go, well, I'll just pick the best diamond and then I'll think of the other components independently. Onto the diamond itself, the 3 things that we focus on are the spin lifetime, the sort of contrast, and the diamond geometry. And there are various different parameters that affect them, and I'll talk about some of them in the next few slides. So how do we grow our diamond? So we use a process called chemical vapor deposition. So in chemical vapor deposition, what we use is a mixture of gases, so typically hydrogen and a carbon-containing gas such as methane. Hydrogen actually plays a key role in that process, and what we do is, using microwave, break up that hydrogen. That then creates this plasma. So this is our example of our schematic of our chambers. So we create this plasma, this big ball of light which sits across above our substrates, so our substrates being diamond seeds. In the plasma, the hydrogen, as I said, plays a key role. So first of all, it terminates the surface. It creates the growth species. So if we see, for example, in a second, we'll have a methane molecule which gets broken up by hydrogen to form a methyl radical. That then comes onto the surface and then builds the diamond kind of layer by layer. And in the corner here, we can see a little video of diamond growing, a speeded up video. And by changing the power and pressure, the gas mixtures, so adding things like nitrogen to adding the nitrogen for the DNB defect, and selecting the substrate carefully, you can change the properties of the material that you're growing. So leading on to actually thinking about what that means in terms of the material and the things you need to consider. As I said, you need to think about the nitrogen concentration and also the NV concentration as a sort of a couple, because that's going to affect what you're going to think about when you're building your device. You need to maximize T2 star, the spin lifetime, and that has many parameters such as the nitrogen concentration in the material, and strain is actually quite critical, and I'll go into that in the next few slides. So we need to start thinking about optimizing all these things, and ideally, so this plot here, spin lifetime versus nitrogen, we want to sit on the line or somewhere on the line, depending on the nitrogen content, the carbon-13 content, because that then indicates we've made the material as sort of as good as you can get. If we're sitting down here, that means there's some parasitic thing in the material which is affecting the spin lifetime. So now I'm going to give you a couple of examples of the material that we're making. I'll start with our 16 ppm material we've developed. So this is sort of more for the single pass sort of technique that I mentioned earlier. And one of the big challenges to think about when you're growing CVD, you're growing this non-diamond stable regime, so you get other defects in the material which can contribute to absorption in the material. And this typically manifests itself, you'll see a sort of a brown coloration. And what we've done is explored lots of different conditions to help minimize and reduce these absorption features. So these are two different samples grown under different conditions where we've optimized the conditions basically to get around sort of about 20 parts per million of nitrogen. But what you can see is we get only in this sample here, we only get a small fraction of neutral nitrogen, the rest of it being positively charged. And this leads to this brown coloration. But by changing the conditions, we're able to actually minimize those defects, reduce the amount of these what we call X, these sort of brown defects, things like nitrogen multi-vacancy clusters, things like NVH. And by tuning the material, the synthesis properties, we're able to, synthesis conditions, we're able to then tune these defects in the material. And you can also see this, there's a strong correlation between the lightness of the material, so 0 being black and 100 being white, and the ratio of the neutral to total nitrogen in the material. So the next thing we've got to do, we want to make a batch process. We want to make a process which is consistent, and this is what we've done here. So this is this batch of material. I've measured the nitrogen concentration, and we can show across a large batch of material, we can make a consistent material. We then go on to irradiate that and anneal that. So typically in as-grown material, you get a nitrogen concentration of about 300 to 1. So in this material, we therefore want to increase that nitrogen concentration and make it more optimized for the applications. And by doing that, by radiating and annealing, we create about 3.8 ppm of NV in the material, gives it this nice purple color. And that had basically 4% variation across this large batch of materials, a large batch of samples. There's 24 samples here. And the idea from what we're trying to do is make this process so we can make it as consistent as possible. So then when we supply material, we were able to do it in volume. So the next important thing is obviously the spin lifetime. So we've made this nice material. What is its spin lifetime? And what's the effect on strain? And this is quite an important factor. So what you see here is a sample which, this is a birefringence image So this scale bar goes from 0 to 10 to the minus 4. And the color basically shows variation in the birefringence in the material. And this, by doing a T2 star maps, this is work of Ronald Woolsworth's group in Maryland. And in this area here, where the strain is low, we see sort of a small variation of spin lifetime. But in this area where there's lots of change in strain, we see it change from 0.36 microseconds to 0.89. So clearly it's very important to be able to control strain. And that's what we're able to do with this particular recipe by carefully selecting the substrates, by carefully preparing the surface. We're able to minimize the strain down into sort of 10 to the minus 6, which then leads to a strain shift of around 25 kilohertz. So this map here is basically a strain map, again performed by Ron's group. So this means we're then able to produce a material which has very uniform properties with a T2 star above a microsecond, so around 1.2 to 1.5 microseconds. So that's the sort of the top end, sort of 16 ppm. We also make material at the 1 ppm range. So again, this is a material that actually that's now commercially available. So we developed this for the sort of multi-pass sort of techniques, where we're looking at sort of 800 ppm of nitrogen. Again, we've done all the similar sort of experiments looking at ability to control the MV concentration. So this has around 180 parts per million. Low birefringence, which obviously leads to low strain in the material. And this material typically has around 900 nanoseconds of spin lifetime, which is limited by the fact that it's a natural abundance material. And as I mentioned, this is the first material that we've launched as part of a series of materials called the DNB series. So just a brief summary of that material that we've made. So we've been developing a range of different materials, and we launched our first general purpose CVD grade diamond, part of the DNB series. And where it sits on this plot that I mentioned there, it's basically on the line for both of these points. We also have another product out there, it's electronic grade diamond, which has a much lower nitrogen concentration. So we're talking single defects. So some of the work, for example, that Andrew might be talking about today, where he'd be looking at controlling single MV defects, this sort of material is more suitable for that sort of application. But we also do a lot of other R&D work. So we're developing carbon-12 processes at a range of different concentrations, and working with our partners to sort of optimize it for different applications. Lastly, I'll just comment, you can also do this in layers, less relevant for sort of the more mobile applications, but things like if you want to do magnetic field imaging, for things like proteomics, this kind of material is also useful for that. Okay, so now I'll just talk about through a few case studies. So I'll start with denied GPS. So this is a project we've been working on with Lockheed Martin over the past few years. The Earth's crustal magnetic field varies from location to location. It's like a fingerprint. So this sort of image here just shows you sort of the variation. So if you know that variation, you can use that basically as a map to pinpoint where you are on the Earth. The advantage of this is that magnetic variations have the additional benefit they can't be jammed or spoofed. So like a normal GPS system, which relies on an external signal, you can jam that, or you can send duff information, which then leads to it to be tricked. And that obviously, if you can have something that's independent, something that's self-consistent on a platform, that's a much better way to position yourself, a much more secure way. Why is Diamond useful for this? Well, Diamond provides a true vector magnetometer compared to alternative approaches. So I mentioned earlier that Diamond has sort of 4 different orientations of the MV defect. So you can use all of those and build up a true 3D vector map. Lockheed Martin have developed this sort of fully mobile magnetometer and really taken it from the sort of the bench into sort of a device that they can put on a ship, and they've done this And this photo here is their sort of first demonstrator system, and it's a relatively compact system. It has a low size, weight, and power, which is a critical requirement for many of these things. If you're, say, thinking about sticking it on a drone, for example. So its weight is 4 kilograms, and it only uses 5 watts of power in total. The other advantage of Diamond here in this particular application, it also has a large dynamic range. That means it can basically sense magnetic fields. And you don't have to worry about the sort of background magnetic field so much. You can do it in low fields and high fields, whereas other sort of magnetometers can suffer from the fact you can only work in a low field environment. And I mentioned Lockheed, they've already developed using this on doing field trials with this system, and they've got a sort of route to also minimize this system and improve it going forwards. So my next application is a much earlier stage. It's about using portable masers, and this is work that we've been doing with Imperial College. And so masers, they've been around for a long time, since 1950s. Way before lasers came online, but obviously masers are not as ubiquitous as the laser. This is partly due to the limitations in maser technology. Typically, you have to use cryogenics or vacuum systems, so making mobile systems much more challenging. And that means they've only really been used in things like astronomy, so as low noise amplifiers, or frequency standards such as in atomic clocks. However, the great work at Imperial, they developed for the first time a solid state maser in 2012 based on a organic compound called pentacene. But the issue they found with that is that because it's an organic compound and you need to pump it quite hard with light to get it to maze, it breaks down. So they could only ever run it in a pulsed mode. That's when they came to us. They saw what you could do with Diamond. And Diamond, if you're not aware, has the highest thermal conductivity of any material. And that's actually one of the other things our company does. There's a lot of material for Diamond thermal applications. But where the NB Defect comes into this is, again, going back to this energy level. This is the ground state. If you apply this magnetic field and you get a large enough magnetic field, you obviously push this -1 state down below the 0 state, creating a population inversion when you then pump it with a green light. The system itself exactly the same as what I showed you earlier. So you've got your Diamond, you've got a magnetic field large enough to create this population inversion. You pump it with your green light, and it's in some kind of resonator system. So they were able to make a continuous wave maser, so operated at 9.2 gigahertz, and you can obviously adjust that by adjusting the magnetic field frequency, and it had a power of 10 picowatts, which is comparable to a hydrogen maser with a line width of 50 hertz. They use about 400 milliwatts of pumping power, and this actually is a spin temperature of around 2 Kelvin. And now what I find exciting about the Diamond maser is that it has, the real potential to sort of be a very disruptive technology. So you probably wouldn't necessarily want to use it in the same current applications, but potentially creates a new way of thinking about communications and timing systems. Oh, and there's a plot of it. Amazing, that's peak. So on to my last case study, which is geosurveying. So mining companies are already using squids for tensor gradiometer to find new mining sites. And the real benefit here is you're able to more pinpoint where you want to drill and therefore sort of reduce cost and reduce harm to the environment. But squids as a technology for geosurveying is actually quite challenging. It's a very bulky technology. So you can see this helicopter here has a large boom where your squid system sits on the end of that boom. You use cryogenics for squids, and obviously most mining is actually done in very remote locations. So handling cryogenics, transporting cryogenics is a challenging process. And also there's safety issues with low flying. Typically they fly 10 to 30 meters above the ground, and obviously that creates a lot of challenge when you've got a boom sticking out of your helicopter. So if you can make a much smaller, compact system which doesn't rely on cryogenics, that's a significant advantage. So this is work that SP Quantum are doing, based in Canada. So they're developing diamond magnetometers for mining, and that's the real benefit here. Again, is going back to what I mentioned about vector capability. So you've got this system that allows you to have vector capability, and the advantage of that then is that you can build up a tensor gradiometer. So instead of just getting single data points, you can get a multi data point system, an array of using an array of sensors, and that allows you to get a lot more information that you typically get using a standard magnetometer system. So, for example, you get more information that allow you to detect, estimate volumes of material that you want to mine, and also detect geological faults. So, in summary then, hopefully I've told you about why diamonds are a unique material for quantum technologies, and I've given you a flavour of some of the work that we've been doing towards making a scalable processes, as well as mentioning our launch of our new material, DNB B1 and the DNB series, which hopefully is helping enable people to get hands on diamonds, develop new systems. And also that they're, it's a really exciting time that there are several new applications on the horizon, which really pushing the boundaries of existing applications, or really enabling new markets. So it just leaves me to say thank you very much for listening, and also thank you to our partners and various funding agencies. I'm taking a little bit too long.
Thank you so much. So I think we now have time for a couple of questions. So the first one is about the quantum diamond grades you talked about. So you said that DNB B1 is already commercially available in the market and is part of the DNB series. Are you planning to launch new quantum diamond grades in 2021? And what are the key challenges in diamond engineering?
Okay, so I think there's two questions there. So the first question being, I'll be planning to launch new materials. Definitely, really what we want to be able to do is get as much diamond out there as possible to our various partners that we're working with, and people that are developing this technology, to allow them to accelerate the development. If they haven't got the material, they can't develop the systems. So this year we're planning on launching two new materials. So one of them is sort of an extension of existing material. So our electronic grade diamond, which I talked about earlier, we're launching a thin plate. So basically it's about 50 micron plate of diamond, which then is mostly for the sort of quantum computing type applications or fabrication areas. And then the other one, we're going to also launch another bulk material to complement the DNB B1 that's already out there. And now I've forgotten the second part of the question that you asked. What are the key challenges in diamond engineering? Well, the challenges, I think one of the biggest challenges, obviously, I talked about reproducibility. I think having that level of reproducibility to combining both the nitrogen, getting the nitrogen concentrations just so it's reproducible, and also the strain in the material, because that can have a very dramatic effect on the properties of the material.
So we've seen from the slides that you just shared, Matthew, that partnerships are really important in making these projects happen. How would you describe the ideal partnership for you and for Element 6? Okay, so
I think it's very critical to have good partnerships and work with people. I think for me, it's really about having it's kind of, obviously it's in the word itself, it's the partnership, working together as a team to solve the problems, rather than throwing a lump of diamond over the wall to somebody. You've got to work with them to understand their problems, and so it's that sort of back and forth that I think really makes a big difference in the partnerships.
Fantastic, thank you. And now I see we have a live question from Philip Schreiner. Apologies if I've mispronounced your surname. Are you also planning to fabricate diamond membranes on, for example, SiO2 or Si wafers for integrated photonic applications?
It's a very good question. I mean, obviously integration, and that's one of the challenges of Diamond, you know, how you integrate it into systems. Things like that are definitely key, and there's some great work. I think MIT recently had done some really nice work at looking at integrating, using Diamond chips and integrating it into more traditional semiconductor technologies. At the moment, I think for us, it's the initial stages, just getting thin diamond plates out there so that it's easier for people to access the material. But certainly things like improving the integration is something definitely that's on our roadmap.
Fantastic. And I think we have time for one last question. So you went through some examples of mobile applications. What are the other quantum-related applications that can be enabled by Diamond?
Also a brilliant question. There's loads of work going on at the moment. So I think last QBN we had Qnami. So they were talking about their work where they were using element 6 diamond as a basically tip, a magnetic tip for scanning magnetic field magnetometer. So they're able to build up the magnetic field on the surface of a material. We also work with other companies. There's another company in Germany that we work with called Envision that basically, and we're involved in a European project with those guys developing systems for medical applications. So basically, ways that you can use diamond to basically enhance other materials. So you basically can convert that spin out to the diamond to do something called hyperpolarization. That basically increasing the sensitivity, say if you want to detect something within a cell or something like that.
Fantastic. Thank you so much, Matthew. And now back to you, Johannes, to introduce our next speaker.
Yeah, thank you so much, Matthew, for this great insights. It was really impressive. So, okay, then we will go to the next speaker. He is Ingolf Wittmann. Ingolf was IBM Technical Director in charge of high-performance computing in Europe and heads the global technical team of IBM Quantum Ambassadors. And now he is head of the business unit Quantum Systems at the Fraunhofer Institute of Applied Solid-State Physics in Freiburg. And he will give a talk on building quantum solutions for diamonds. Ingolf, the virtual stage is yours.
Okay, thank you very much. So I try to share my presentation. Okay, here we are.
Perfect.
So thank you for the nice introduction, Johannes. And what I like to cover today is I like to talk about today's quantum systems, how they are looking like, what their challenges for mobile solutions, and how hybrid approaches from the big IT system environments could help here on a small scale. And next then is an example within the mobile phone arena. And last but not least, knowing all of that, diamonds are not only the girl's best friend to build qubits and registers in a mobile environment. That's also a good possibility. And Matthew was already introducing quite nicely how this is looking like in an academic environment. So just a short introduction around the Fraunhofer organization. The Fraunhofer IAF is an institute for applied physics in Freiburg, and it's one of the oldest institutes within the Fraunhofer organization with over 70 institutes and more than roughly 30,000 employees. In Freiburg, we are roughly 285 people taking care about technology within the applied physics environment. And one of our research areas are diamond defect centers for quantum magnetometry and single photon sources. We are also one of the 7 leading institutes within the Fraunhofer Competence Network for Quantum Computing and running the Quantum Computing Competence Center Baden-Württemberg. And our focus areas are quantum computing hardware and software interfaces. So the next level in that environment. So when we are talking about quantum computing, we are talking today about big system environments, at least like the IBM Q System 1, which is actually installed in Germany in Eningen as part of the IBM Fraunhofer collaboration. And this system is having a quite big footprint of roughly 10 square meters and power consumption of 10 kilowatts. And if you would like to run this type of system within a quantum simulator, you would need a size of a couple of 100 square meters and roughly 1 megawatt in power from classical HPC systems. So within that already this type of quantum systems having an advantage in terms of footprint and energy consumption. And this is the first commercial system outside US with 27 qubits. And the target is 64 and quantum volume of 64. The system was readily installed before Christmas last year and handed over to Fraunhofer in January. And the calibration is still going on. And we are going forward really to achieve these 64, the quantum volume of 64. We are talking today about mobile quantum computing. So why will this technology not fit into a mobile approach? And this is obvious in the first step. It's because of size and it's because of energy consumption. And this is even a problem within the classical quantum computing environment. And that is one of the reasons why HPC centers, but also companies who like to use quantum technology are looking for hybrid quantum architectures. On the one side, we are having this classical environment with the fabrics like Mellanox, FPGAs, GPUs, and flash systems, which are combined to big system environments. And in between, you need somehow a classical CPU, a processor, which is really combining all these different piece parts together and deploying all the workload on the different components within a proper software stack. On the one side, this is limited. We cannot grow that very much in the future. And that's one of the reasons why the research environments and companies are looking for new approaches. And new approaches are non-von Neumann architectures like on the right side. So neuromorphic designs like the synapse chip from IBM, but also quantum technologies might fit here in that environment. And you can use those technology like accelerators like on the left side, which are combined and integrated within an HPC environment. And you need the full software stack also for that. So from the hardware piece parts over the operating systems to the distributed workload management, and then the applications who are really supporting these different types of piece parts. And when we are talking about energy consumption, for example, the synapse chip, it's running with 1 million neurons, having roughly 256 million programmable synapses, and there's no clock, and that's really quite interesting. And you can run 46 billion synaptic operation per second. And the interesting part here is that is done by 70 milliwatts. So this is really fitting within mobile environments. On a bigger scale, we can look on quantum technology, how to integrate that. And a good example is the IBM System 1, which is integrated in the Oak Ridge system, HPC Oak Ridge system, as such as an accelerator. But when we like to go down in a mobile environment, those big system environments are not fitting, and we have to think about a different approach here in that environment. So current challenges for the quantum computing environment in such type of environments. So transform qubits, and that's the most used technology within the quantum computing environment today. You need really a cool environment, roughly with 50 millikelvins. And you need also, or the compute time is really limited to 100 plus milliseconds. And the systems are becoming bigger. On the picture on the left below, you see the first example of IBM how to build a 1000 qubit system. And 1000 qubits means you do have 2000 microwave lines into the choreograph to manipulate the different qubits. 1000 for initializing and to manipulate them, and 1000 to do the readout after the calculation. And that's quite challenging, because with that also the temperature environment is affected by that. And we have to think how to do that differently in the future. And maybe also the optic environment and what we are doing within the diamond environment could help to integrate all this type of technology within the choreograph, and having only a couple of lines to the outside area. But this is not really working within the mobile environment. When we are talking about mobile environment, most of the people are thinking about mobile phones or something like that. But when we are talking about mobile environment, we are talking about separated systems, and mobile in a first step could be cars, could be trains, could be airplanes, but on the other side also something like satellites, or in the medical environment, MR systems, or for traffic control system, especially air traffic control systems in the radar environment. And when we are thinking about how to integrate quantum technologies on the right side, this is quite interesting. You can really think about any type of industry where you can find an area where mobile quantum computing can help, can improve, or even make solutions available which are actually not possible. And when I was running quantum industry use case workshops with a lot of clients during my IBM time, in every meeting I was identifying new application areas for quantum computing, and also for the mobile environment. Even in the telecommunication environment, when we are talking about infrastructure, so transmission masts, and there are tens of thousands of them everywhere over the world. There you have small compute centers at the bottom, where the routing of the packages and optimization of the communication is done. And even there are use cases where you can look for quantum technology. A good example here is the newest announced Samsung mobile quantum technology. Samsung was announcing at the end of 2020 a first mobile quantum solution together with ID Quantique, a Swiss company, and SK Telecom, that's a big South Korean telco provider, creating the first mobile phone with quantum technology. The quantum chip on the left side is pretty small. It's just 2.5 by 2.5 square millimeters in size, and using LED sources of light to generate photons. Then the CMOS sensor detects the photons, and the number of the photons detected within a certain sensor area for a certain time is unpredictable and according to the laws of physics. And there is and that's used as a random number generator, which is a severe problem within the classical computing environment, because random number generators are not really random number generators. So the quantum random number generator chip is built in a Samsung Galaxy A quantum system, which is renamed meanwhile to Samsung Galaxy A71 5G, and you see the picture on the right side, and that's really available, and it's proven random regarding the numbers which are generated here from that chip. But that's only the important part of the technology. What you really need is then the whole environment to support that. And SK Telecom is providing the software stack and the IT infrastructure of the quantum key distribution system. Those generated true random numbers can be used for two-factor authentication, for single sign-on, for biometric authentication, for example, the SK payment system, along with blockchain-based wallets to store secure electronic documents and certificates, for example, insurance claims. So that's really needed to make the technology working in a production environment. And nobody of the users, or there's a limited amount of people, of users of that mobile phone, is really having a clue about quantum technology. So everything is hidden within the whole environment. But this solution is not covering any computation parts like quantum AI for pattern matching or global positioning systems. And for that, we really need a real quantum processor with a reasonable amount of qubits. And we are not talking about thousands of qubits for dedicated black box environments. Even a small amount of qubits might help you on that. So, and there the diamonds are coming into the play, and Markham was already talking about the technology and how this is working. And that's exactly also the field where the Fraunhofer IF in Freiburg is working on it. We are producing and growing industry diamonds with these nitrogen-vacancy centers since a couple of years quite successfully. And mostly those were used within the sensing environment, in the health arena, but also to figure out problems within chips which are produced, where the power lines, for example, really carrying power or not, or if there's a defect within the chip. For quantum computing, there are some additional challenges with the diamonds. So how to entangle several of those spins or building qubits out of that, and to perform at the end quantum gate operations. And important also are other competencies for exploitation of these quantum technology. On the one hand, the material development in the diamond field, but also above all the expertise in optoelectronics and microwave technology, which must be used for the excitation of the color centers on an atomic scale. And further development has to be done on that, especially not by just one organization or a couple of people. Really, we have to have a community here in place. And on the other side, additional skills are needed, for example, in the cryotechnology and optical characterization. And we are facing that topic really also on the Fraunhofer IIF when we are looking for experts and people who can work here really on that. Okay, so how to build out of an diamonds and qubit. So a Q node, that's the smallest environment. So within a diamond, and or a Q node is representing a diamond with one color center, and then is representing one qubit. What you can also think about that is to build more than one vacancy center within one diamond to have, for example, two qubits, for example, in one diamond. But that's really a challenge, and how to manipulate that, how to control that, even in the beginning, how to grow that, and really to have those vacancy centers within one diamond. But nevertheless, even if you are having one vacancy center in a diamond, or a couple of them, out of them you can then start to build registers. And that's the interesting part, to build, to combine different diamonds with a specific optical network, or within an nanowired array, to combine 9 diamonds or 9 qubits or even more. And that's something which has to be figured out, how this can look like, how this can be managed, and how this can really be produced. And on a bigger scale, then you can combine a couple of these Q node registers in a multiple node array, coupling those different registers with an optical coupling environment. So that's just an idea how to build quantum registers or small-scale processors on that. And as I mentioned, for some of the application, you really do not need hundreds of qubits. In some of the use case arenas, maybe there are 10, 20, or 30 qubits good enough to run a possible application. And that's something what we are actually doing within a project in Baden-Württemberg. So the state of Baden-Württemberg was rewarding funds to different consortia, and one of the consortia is the QC for BW, that means quantum computing for Baden-Württemberg, where we are looking for our first diamond-based register based on spintonic technology to build a scalable quantum process at the end. And it was already mentioned, you cannot do that by your own alone. There's a community needed, and the consortium which is really working on that is Fraunhofer ICT, CKIT in Karlsruhe, University of Stuttgart, University of Ulm, and University of Constance, and led by the Fraunhofer IIF Institute in Freiburg. And we got LOIs of industry partners, and the associate partners are separated because only the academic environment was rewarded with funds and money to build that up, but the associated partners are interested really on our work and can actively also provide input and be part of the discussion, and can follow the project and maybe support us also with some ideas really to build up such type of technology. So within the next couple of years, next 3 years, our intention is really to build a first diamond-based register which can be used for quantum computing. And it's also including the whole software stack. So it's not only just to build the register, you have to build the environment with a software stack to support this. And this is then on a longer scale really to build a full stack quantum system, not just within register, but also with a quantum computing environment which can be used also on a bigger scale. So the base technology is built within, like the QC for a BW project, but there are also upcoming calls from the BMBF, so the German Science Ministry. We are expecting those in February for some lighthouse projects which are looking for a full stack of technology from the base technology beside transmon qubits up to the application environment on the right side. And the people organization have to build consortia really to cover everything and have to show up the value and also within a 3-year time frame what they really can achieve in such type of environment. And diamonds might be here also one of the technology which are fitting in, and maybe also in combination with other quantum technologies. Okay, that's it from my side. So if you are interested in more or having any questions, feel free to contact me. Also, if you are interested in using quantum environments and systems on a diamond-based environment, we are happy to discuss, especially when we are talking about any type of cooperation. And with that, back to you, Johannes.
Yeah, thank you very much, Ingolf. I always dreamed of a signet ring with a diamond included in it, with a quantum register to unlock my data storage or my laptop or so on. This would be perfect. Yeah, so Gabriela, do we have any questions?
Yeah, so the first one. So thank you so much, Ingolf, and amazing to see how Diamond is unlocking so many technologies in so many areas. So you went through the case studies of the projects you're currently working on. What are the next steps in order to turn those projects into actual products? And when can we expect to see some of those products being launched in the market?
Okay, so there are a couple of questions within that question. So we still have to figure out the full capabilities of diamonds. And there are a lot of problems have to be solved. We also have to figure out where diamonds are better suited than transmon qubits, for example. Or even an obvious area is room temperature, for example, room temperature environments. So when we are talking about mobile environments, you cannot run with 50 millikelvins. But also an interesting topic here is hybrid quantum technologies. So to combine different type of quantum technology, like diamonds with transport qubits, or when we are talking about quantum AI, this is really the biggest problem is to get data in. So you need quantum sensing that the states are already in quantum state. And then you have to store these states. So quantum memory is also a technology. And computation could be done maybe with transform qubits. So the sensing and the memory might be a different type of technology than the transform computes. But combining all these technology, maybe we have really a solution within quantum AI.
Thank you, Ingolf. And speaking of partnerships, so similarly to what Matthew went through, you as well explained how partnerships are so important in the projects you work on. You mentioned Samsung and a range of other partners. What does the ideal collaboration partner look like for the Fraunhofer Institute?
So in a first step, most of the projects we are doing within our environment, within the academic environment, are government funded. So that means partners are moving and doing their work also in that type of environment. So we are looking for academic institutes, universities who are doing base research within the quantum environment, but we are looking also on organizations who are just in between, like the Fraunhofer Institute, who are taking the base research and moving up from the technology level to the first prototypes and handing over those prototypes then for production within the industry. So all these three, let's say, levels and partners are needed really to build functional and working environments. And the interesting part within Germany actually is that the government funds are moving also in the direction that industry partners are rewarded and can be incorporated within such type of projects without putting a lot of money within such type of projects. So we need, so such type of projects needs different type of expertise, combining those together and really to build something out of that. And those platforms like the Quantum Business Network are excellent platforms really to figure out who is in the market, with whom you can cooperate. But also you have to approach other parties and like I was asking, approach us if you have interest or if you're having an idea, and then we can start to discuss and to work.
That's fantastic. Thank you, Ingolf. And definitely very promising trends, particularly in Germany, leading the way and investing so heavily into the quantum world and quantum technologies. So we have two questions over there for Matthew, so we can tackle them at the end of the session. So one last question for you, Ingolf. There is the potential to integrate the technology you talked about in so many areas and so many industries. Are there any non-mobile but still diamond-enabled applications that you can quickly tell us about?
Typically, I would think about in a first step about black boxes environment. So you will not have in the classical quantum computing environment the perfect quantum computer as such in the next couple of 5 to 10 years maybe. But what you can look for is really to build physical infrastructure environments suited to a very specific problem, like we have seen it within Samsung project for the quantum random number generator. And I think that's the first environment where we will see, let's say, economic solutions which can be sold also to clients. And we already see that within the security environment and within the random number generator. So we have to look for the next level, so more complex application where maybe very specific molecule calculation is done, or like the example from Matthew, exploring the surface for drilling, and then to build a very specific software stack on it to build the application, and then the application is put into the system like an EEPROM. And when you need changes to the system environment, you have to rewrite the EEPROM with the application for that. And maybe that are the first areas within mobile environments, but also for the classical quantum computing environment.
Fantastic. Thank you so much, Ingo. Very insightful. And now back to you, Johannes, to introduce our last speaker.
Yes, thank you very much. Just want to add one thing. You talked about potential partners, mainly from Germany. I think there will be also a lot of European calls from the European Commission in this year and the next year. So
yeah,
I think
absolutely.
we have to focus on Germany, but also on Europe. Okay, yeah, now I'm more than curious to learn more about quantum at the edge applications of closed web quantum computers by Andrew Hosley. He is CEO and co-founder of Quantum Brilliance. He is a quantum scientist and engineer and has worked between Australia, Switzerland, and Germany, and led the experimental Diamond quantum computing efforts at the Australian National University prior to funding Quantum Brilliance. Andrew, the stage is yours.
Thanks so much, Johannes, and yeah, thanks to yourself and Gabriella for organising such a great event, and always a pleasure to be with then Matthew and Ingolf as well. So, you know, we talked about ideal partners, and these guys are certainly the some of the key ones that Quantum Brilliance has been working with. So we're a company based in Australia, but also working in Europe, and we're about making quantum computing something that is just another everyday technology. So rather than being something that's confined to large facilities and is something that you really only touch remotely, it's something that is just like any other component of a computer. So we've got then products that we'll have coming out this year, which is actual quantum hardware, and I'll talk to that in a sec. But then also our goal is to, in 5 years, have a box that actually solves your problems faster. So a quantum accelerator card that gives you quantum advantage relative to a device of similar size, weight, and power. So having something around 50 qubits and giving you this, for certain applications, supercomputer level performance in a GPU form factor. So we'll talk more about those, but the key thing there is that we're coming out from then a real 2 centres of strength in diamond technologies and science. So the Australian National University, as well as then Southern Germany, and these are our 2 bases of operations. So my technical co-founder, Marcus, is here today as well with us. Together then we've founded Quantum Brilliance along with Mark Lowe, who's comes in from a business development side of things. And we're currently about a team of 20 people based between those 2 countries. So, and just to flag there that the German efforts are really building up a full stack. So we're really in the early stages now, but the goal is to have then R&D through to manufacturing as well as our service delivery. And in that context of full stack as well, is that we're actually really a full stack quantum computing company. So we're about then going from the qubits all the way through to then software and applications. And we're developing that with a whole ecosystem of partners, both in the high performance computing sector, as well as in machine learning and other quantum applications companies. And so an example of that is then a very close partnership we have with the Pawsey Supercomputing Centre here in Australia, which is one of the tier 1 centres here. And with this, we're then building software that allows us to integrate into other systems and applications that let us take advantage of a very unique vision for quantum computing that we have, this everyday technology. So I think we'd all agree that quantum is something that is a computing technology that takes us well beyond anything that a classical computer can for certain applications. And we've seen this now in a couple of cases in China and the US, where a single quantum processor with only a few tens of quantum bits is able to outperform the world's largest supercomputers for certain tasks. The challenge is that these things are really taking us back to mainframe era. So like the 1950s and 60s, they're big machines, they take up a room, they have a huge amount of infrastructure requirements. You can't just put them down in any building. Often you have to build a specialized building to house a quantum computer. And so it's something that's going to really be incredibly important and transform industries in that vision, but also be fundamentally confined in terms of the applications that it can support. And just like many businesses at the moment, or various sectors require a local computing solution, you can't go to the cloud for everything at the moment, then quantum is going to be similar. And so cloud quantum computing is only going to be able to support a certain subset of the full application space that it might be able to. Now, another key thing is, at the end of the day, we're trying to build something that isn't just cool, but actually does something useful. And so there's a lot of different definitions of quantum advantage. But what we work with is then the point when you have two comparable devices of size, weight, and power, and one does better than the other. And so then that threshold of quantum advantage is actually a sliding scale depending on the size, weight, power of your computer. And the challenge there is that if we're like using superconducting qubits and having these room-sized devices, then really the comparable is a supercomputer. And so the threshold for quantum advantage is then, depending on the application, in the hundreds or thousands of qubits and beyond. Our technology lets us really scale down the size, weight, power to something smaller than a lunchbox ultimately. And so with that, then that threshold is now more like a laptop computer. And so that really changes that conversation around, okay, what's that threshold and how do I start using these things? And we can actually cross that threshold with even a few tens of qubits. And this is something that we'll have a look at in this talk. And that's not where we end. Crucially, we still scale up to hundreds and thousands of qubits and beyond. But we're now doing that in this regime of quantum advantage. We're providing people with devices that aren't just about getting ready for quantum, but actually are solving problems and then reaching a much wider market. And so just like then in classical computing, we had the microprocessor come in the 1970s and really transform what computing could be and turned it into this ubiquitous everyday technology. We're looking to do the same with quantum, using room temperature diamond microprocessors to create a technology that anyone can use and is similarly robust as today's classical devices. So we've then had some great introductions today from Ingolf and Matthew about exactly what's under the hood there. So we've got a nitrogen vacancy center at the core of our device. So we've got spin qubits, just like the spin qubits in a trapped ion or neutral atom computer. And the difference here is now that they're trapped inside a diamond crystal lattice. And what that means is that both from that trapping and the extreme properties of diamond, we really front load all of that complexity into the fabrication of this device. And then we have something where the spins are able to sit in that diamond at room temperature and provide us with that quantum resource without any further active isolation of that system from the environment. So it's just like your laptop. It's a complex fabrication process, but then you send out something very robust and simple into the world. And the control simplicity of diamond that Ingolf and Matthew also touched on today is that then you can really miniaturize the lasers, the electronics that go around this as well, and so have that pathway to devices that fit inside many everyday technologies. So there's two things that really changes in terms of the narrative about quantum. One is now we take it out into the world. So it's not confined to big facilities, but now you can have it under your desk, you can have it in a self-driving car, or you can even put it up in satellite. And we'll talk through then one set of use cases there. Another set of use cases I want to talk to as well is actually around that centralized model as well, and how this miniaturization changes how we think about then quantum computing in supercomputers and data centers. And we now have this opportunity to, instead of having 1 or 2 quantum computers in the next room, we can have thousands of quantum computers, just like we have thousands of GPUs, thousands of CPUs, and they're filling a similar form factor in the racks alongside all of the other components of your supercomputer. So before I then talk about those specific applications, I just wanted to pause and have a look at the tools that Quantum Brilliance is now building to explore these. So I mentioned at the start, we've got then quantum hardware coming out this year. So that's based around, in the first instance, a single NV center in a rack-mounted unit. So we can have up to 5 qubits to actually explore systems integration and have a hands-on on-site access to an actual quantum computer. We're also then building a quantum emulator that efficiently simulates this, and we can then scale up on computing systems to larger numbers of qubits and so explore a wider region. And above that, we've then got a accelerator operation-oriented operating system that we're developing in collaboration with Oak Ridge National Labs in the States. And so that's something that then is aimed to allow us to efficiently make use of the quantum resource that we're building here. Now, the really interesting thing here is by shrinking down that size, weight, power, and so we've got this very different definition or threshold rather for what quantum advantage can be. The threshold is now about beating the components of a supercomputer rather than the supercomputer itself. And so we can actually use a supercomputer to explore quite a wide region of quantum advantage in the case of our particular hardware. And so this tool set of quantum emulator and quantum operating system is actually something that then is far more powerful than the equivalents that you would be able to explore with any other quantum computing platform, and that we're able to then actually explore the real use cases, and these are the projects that we're working on at the moment, explore these use cases that I'll talk about and push them to not just toy models, but beyond into actual applications. So we haven't got there yet, but these are the kinds of things we're looking at. So one is looking at quantum applications at the edge of a network. So the edge of a network is places that are far from then a centralized facility. That might still be in your home. But it can also then be in a remote place. It can be Internet of Things. It can be then a remote monitoring facility. It can be up in a satellite, or it can be even in a self-driving car. There's the particular applications here that I want to talk about around kind of image processing and signal processing. So there's many applications where we want to monitor an area. And so this might be for search and rescue operations. There might be a defense application, or it might be a farmer who's monitoring crops or livestock. And we want to automate the analysis of that data. So the farmer, for example, doesn't generally want hours of live stream of her sheep walking around a paddock, but she might want to know how many of her sheep have gone to the dam for a drink of water that day. Or maybe she wants to know how many ewes have been visited by her stud ram and in what order. So we need to take a vast amount of input data and perform a context-aware analysis to return high-level information to a human so that they can make then an informed decision. What we're doing then in these applications is processing signals and images to identify features and then the most likely sequence of events that happened across those signals. So this typically involves putting data into a trained neural network, and that neural network is then outputting a highly correlated set of results that then require further processing to reveal that most likely sequence of events. Now, the neural network step is actually generally quite well optimized, but that subsequent step can be a real bottleneck. And The challenge there is that classical solutions are quite inefficient at dealing with the combinatorial explosion of possibilities and correlations between all of those different events at different times. So that you have then an exponential scaling of resources that's required there. This is a particular problem that's challenging in edge computing, like in a satellite, where computational resources are constrained rather. So you have then severe limits on the size weight power package that you can put up into a satellite. And so you really need to work with quite limited resources there. And then depending on the application, you might also have very tight timing restrictions as well. Now, to get around this, people introduce a lot of severe approximations. So they really restrict the scope of that problem and introduce then quite large inaccuracies. And for example, they'd only consider a small chunk of that output data at a time. And these chunks can be surprisingly small. So often they max out at even 4 events. So what that means is we're then ignoring all the correlations between those chunks. And remember, this is highly correlated data. So a lot of the really important information that we're trying to extract is these correlations. So imagine if you had to decipher this word whilst only being able to look at those chunks of 4 letters. Deriving meaning from those small chunks of blue data is a much harder problem than reading that entire word as one. And in many analysis cases, this kind of restriction of breaking things up into tiny, tiny chunks means the output will be garbage. Or even worse, the output will be something that's completely false but won't flag an error. And this lack of accuracy is a major problem for potential users. And so we need to find a way to assess a larger number of events at once. Now, fortunately, this kind of combinatorial explosion caused by those correlated possibilities is exactly one of the things that quantum computers are good at. And so what we're exploring is then a hybrid machine learning quantum decoder, where a quantum computer is used to process the output from the neural network. And this lets us process larger chunks of data, of that highly correlated data, right? And so we're able to then use n qubits to address correlations between, depending on the input parameters, n to the 4 to even n over 2 events. So even with 8 qubits, we can match in terms of that chunk size, match existing edge computing resources. And these edge computers aren't, small microprocessors. We're talking about state-of-the-art GPU cards, but there's only space for a single GPU card up there. So what we're able to do is then achieve a dramatic improvement in processing accuracy and speed. And in many cases, actually, it's the accuracy that's critical. So we've got a fixed time budget, let's say it's a second, and we really need to get something out that we can trust within that 1 second period. And by introducing a quantum computer into that final analysis stage, we're able to achieve that required performance goal. The other nice thing about this is then it matches the memory constraints of NICS devices. So we can use the neural net to filter the vast amounts of data that are coming in, so the big images or large signals that are coming in. And that's a real challenge. Typically with NICS devices, as we've alluded to tonight, input-output is the thing that's often swept under the rug, and also the fact that we simply can't store that much data in a quantum system in the near term. So with this, we can filter the large amounts of data, output a small amount of very high quality, highly correlated data that is challenging for a classical computer to address. And we can then use our quantum system to just analyze that, and so output then the desired result. And this is something as well that's interesting, because it means then that we have actually quite a highly reconfigurable system. So we can use then a whole bunch of different neural nets to address different problem classes whilst retaining a single relatively fixed quantum analysis unit there. And so we can apply this from speech to text problems to assigning to text problems through to identification and classification problems, like of people, of animals, of behaviours, or the interactions between different objects there. So this is something that we're currently exploring in a defence context with Australian defence partners, and looking at remote monitoring of areas. So this is one where there's really strong computational restraints in the satellite. There's very big bandwidth limitations, so they have to do the processing on board the satellite, and they really need then high quality, trustworthy data to be sent to troops on the ground as soon as possible. And this allows the troops then to actually receive the data directly, rather than the data having to be beamed back quite slowly via a low bandwidth channel, get analysed at a centralised facility and then beamed back. So these are then some promising applications that we're directly looking at. But as I say, these are a very broad range of applications that filter into things, anything from ad tech to search and rescue. So the other one I really wanted to talk about was, what do we do in the context of centralized computing? So where we've got a data center or a supercomputing center, and now instead of being able to supply with 1 or 2 quantum computers, we can actually supply with hundreds or even thousands of quantum processors. And the particular thing I want to talk through here is quantum chemistry. Now, this is one that we often think of as one of those go-tos for early quantum applications. And a lot of the work has been done in the context of single quantum molecules, where you're able to efficiently simulate then again that highly correlated system of many nuclei and electrons. The challenge there is that, one, in single molecule simulations, the threshold for quantum advantage is probably on the order of hundreds of qubits, not tens. And the other is that we're still only looking at a single molecule. So for many applications, you really need to be looking at ensemble dynamics, whether that's, for example, looking at a catalysis reaction, where reaction byproducts from one molecule then feed into the dynamics of that identical molecule nearby, or where you're looking then at highly correlated systems where you have interacting molecules in a gas, or diffusion through a solid or liquid, or even if you're trying to model extremely large molecules. These are classes of problems where we then need to turn to molecular dynamics, which is the other kind of big subset of chemistry simulations, dividing this at a very high level. So these are all applications that feed into drug discovery, into efficient industrial chemistry processes, into battery storage. There's a whole range of them important and highly economically relevant applications that are happening here. The general challenge for molecular dynamics, though, is that you've got a lot of stuff there. And so to keep track of all of that, generally you have to throw all the quantum out the window. And so it's a set of purely classical interactions, purely classical point-like particles with classical dynamics describing their trajectories. You can go quite a long way there, but one thing that you tend to not be able to do with a purely classical system or model is then look at any of the chemical reactions that are happening. So to do that, you need to be taking into account the internal electronic states of the atoms, so that you can simulate the breaking and forming of chemical bonds as you go through excitations of those states and relaxations. So the way that people often get around that is using a technique called quantum molecular quantum mechanics / molecular mechanics. So you don't simulate your entire system quantum mechanically, but key components, key subsections of your molecule or your sets of molecules, you're able to simulate with a quantum sense, and then the rest you are simulating classically, and you have shells of interaction around that of then how particular classically described atoms feed into the quantum mechanics thing. So this could be, for example, the active component of a large molecule. It could be then the particular binding sites or things like that. The challenge again here, the advantage is we can now, for certain classes of things, start to have that accurate quantum mechanical description that lets us now explore a much wider range of really industrially relevant problems. But we don't have then the ability to really scale that up. So it's still extremely computationally expensive. And this is an iterative process. These computation. So the I'll leave it at that, just to say that they are very expensive computationally. So the nice thing, or what people do already, is then invest in bespoke systems with custom designed chips that are designed just to solve these molecular dynamics problems, and have then high performance computers. Some of them are even entirely based on these application specific circuits to solve these problems. So kind of a natural extension of this is to use, instead of classical application specific circuits to model those quantum systems, we actually use a quantum processor unit to efficiently model the quantum components of these modules. And so now we can have one with just a single quantum computer that's already giving us a speed up, where we can have then, for something supercomputer level performance, for the size, weight, power cost of just a component of that supercomputer. But we can now start to explore, when we've got thousands of quantum processors here, with each CPU having its own accelerator, we can now start to explore really new regimes. And so probe problems that we didn't have the resources to probe before, whether that's then looking at multiple reactions within a system of biomolecules, whether it's looking at certain protein folding activities, which, as we know, is really critical for understanding the functionality of protein, is how that folds. Or it can be looking at then how, at a large scale, the dynamics and the ensemble dynamics of a catalytic reaction take place. And so we're able to then really achieve new efficiencies in industrial processes through our understandings gained there. So the two takeaways out of this are that the vision that quantum brilliance has for quantum computing is around shrinking down the size, weight, power of quantum and taking us away from a mainframe model of computing to one where quantum is just that everyday component of computing, whether that's then taking it out into the world and using it in all the ways that we use a device today in mobile and distributed applications, or whether it's now having thousands of them in a supercomputer. There's now whole new classes of quantum applications problems that we can enable and can already start exploring. And the other really nice thing about this is, because of that low threshold of quantum advantage, we can actually explore some of those regime of quantum advantage using the existing classical supercomputing resources that we have available today. So in terms of then ways that people can engage with us, so we've got then hardware, we've got software and a full quantum software stack, as well as application discovery partnerships that we can work with people on. And then we've got this 5-year partnership pathway to being able to provide quantum advantage to users in that lunchbox form factor. The final thing I'll leave you with is that we're hiring both in Australia and in Germany. So we're looking for quantum engineers in the lab to help drive theory. We're looking for people who can help us explore these quantum applications and work with external partners to understand and come up with new solutions there. And then also business development and management roles in Germany. So please reach out to us if you're interested in learning more about any of those. And thank you all very much.
Fantastic. Thank you so much, Andrew. It's amazing to see the possibilities that are opened up by the miniaturization. And I do look forward, as a bit of a geek, to the point where I'll be able to look at my mobile phone and see a mini quantum computer in it. So I see that we have a few questions from the audience. So there's people who's actually asking for you to keep them posted, Raymond, because they're working on Diamond quantum memory. And then there's a question, Andrew, if your system is based on room temperature and B qubits and uses magnetic dipole coupling between them, how are you going to solve the problems of deterministic fabrication of closely spaced NV centers? And how will you avoid the decoherence from the mutual interactions between them?
Sure. So I can give a high-level cover of that, and we're fortunate to have Marcus, our Chief Scientific Officer, with us today as well, who might be able to expand upon that. But the key is then around carefully engineering the spin environment around these, and so having dopants to stabilize their charge states, and then, for example, applying a gradient magnetic field so that we have individual control of each spin or of each electronic spin. And then it's around, I guess, carefully maintaining that coherence and keeping track. One of the challenges is keeping track of all the phase shifts that then the things that the quantum gates and the actuations there that as that scales up, the different things there. But these are all, I guess, feed-forward techniques that then are complex but quite engineering, quite tractable in an engineering sense.
Amazing, thank you so much. Now, speaking of commercializing the solutions, why would I need a quantum computer in my mobile or in my car? And when will I be able to get it? So when are we likely to see these solutions becoming a reality in the market?
Sure. So I think the mobile is still quite a few years away. The quantum computer in your car is then something that already at that 5-year point will have first prototypes that might be able to be suitable for those kind of applications. And the types of things that we might want there are around that contextual decision making that's so challenging for any type of AI at the moment. So it's, you know, in the context of self-driving cars, it's then, is that kid that's bouncing a ball next to the road about to jump out, or what do I need to be paying attention to? What are the interactions that I can ignore? What are the ones that I really need to then slow down for or take evasive action for? And that contextual understanding is particularly challenging at the moment. And these are the types of problems then that our quantum accelerators are able to help address.
Great, thank you so much. So one last question, then we can cover the two that I asked to Matthew. So we've seen that a common theme across all the presentations is the importance of being part of this global ecosystem, which is the quantum industry and the quantum world. So similarly to what I asked to the other two speakers, how would Quantum Brilliance see their ideal partner look like? Because obviously at the end of the presentation, there was a pretty big call to action about contact us and work with us.
Sure. So, I mean, as well as then the team that we're looking to build and grow internally, then we're looking at a whole range of different partnerships. So as that full stack company, we're looking at partners to help us with the tech development in terms of materials development, in terms of control systems, both in terms of hardware and software, and optimal control solutions. We're then looking to partner with supercomputing centers and look at these systems integrations challenges of how you get quantum systems to integrate into these existing quite complex classical systems. And an interesting extension for us is then extending that to now these mobile and distributed platforms. So then how do you get it working in a ship or a plane or these other complex environments? As well as that then, so it's that full stack, right? Technical partnerships up and down the stack. We're looking then, we've got products in the market and looking at these customer driven partnerships as well. And then, as I mentioned at the start, we certainly see Element 6 and Fraunhofer as some of our core partners as well.
That's great. Thank you so much, Andrew. So now we still have some time to tackle a few more questions before the end of the session. So Matthew, first question for you. Can you give any rough figures of merit for the positional accuracy that could be achieved using the magnetometric position solution?
Okay, so good question. So obviously the design of these systems is for denied GPS application areas, so areas where you typically don't have a signal, or you're worried about signal from a satellite, or you're worried about that signal being compromised. So in that light, you're probably never going to beat traditional GPS systems. You're not going to get that same level of accuracy. However, you know, partners have definitely demonstrated down sort of the order of meters, tens of meters. That sort of level has been demonstrated using magnetic navigation.
Excellent. And another question for you, Matthew. So from Harry Herman from the audience. To obtain absolute coordinates, does it require augmentation by other metrological means, for example, INS, inertial navigation, gravimetry, or some sort of positional point of reference?
That's another good question. Ultimately, yes, because you obviously got the role and pitch of whatever it is that you're traveling in, say it's a plane or a boat. You've got to know the orientation of your magnetometer with respect to the, say something like an INS would be suitable to basically provide you with that knowledge to reference it back. And obviously, I think, Henry, if you've got any more questions, please reach out to us.
Fantastic. Well, thank you so much. Before I give the word back to Johannes, I just want to say thank you to all the speakers. I've definitely learned a lot about quantum technology today. So yeah, thank you to the speakers, and thank you to our audience for being so engaged. Back to you, Johannes.
Yeah, thank you very much, Gabriela, and thanks to all the speakers, Ingolf, Matthew, and Andrew, for your very impressive talks. And yeah, an official welcome to Quantum Brilliance here in Germany. It's great to hear about it. And yeah, at the end of every webinar, of every QBN webinar, I'm learned a lot. And if you think of the fundamental research I did in my diploma thesis and this large setup, and then you think of the case study Matthew presented with the 4-kilogram payload for a drone, for example. Yeah, it's a huge step. It's great to see this. Yeah, I think in general, diamond is a fantastic material for various applications in quantum technologies, from sensing to computing. And yeah, we learned how to engineer these materials and what is important. Why is it a great material for quantum technologies? We saw a few case studies, denied GPS, portable masses, quantum registers, and quantum processors for the future. And I also learned that I need to buy a Samsung mobile device as soon as a diamond is in it for a quantum random number generator. Yeah, thanks again to all the speakers. It was a great webinar. And thank you also, Gabriela, for co-moderating the webinar. Yeah, for everyone else, for all the participants, please do not hesitate to contact the speakers directly or contact me and I can introduce you. If you like the content of QBN, of the webinars, please subscribe to our YouTube channel and also follow us on LinkedIn and Twitter. And yeah, hope to see you in the next QBN webinar or the next QBN meeting or the next European Quantum Leadership session. So stay safe and thanks again to all of you. And yeah, bye-bye.
Thank you. Bye-bye.
Thanks very much, everybody.
Thanks. Bye, everyone.